Hello guys, in this video we will discuss a solution to the problem maximize the root which appeared in the educational Codeforces round 168 rated for Def 2. So in this problem it is given that we are given a rooted a tree consisting of n vertices. The vertices in the tree are numbered from 1 to n and the root is at the vertex 1. The value ai is written at the ith vertex. So every vertex has a corresponding value ai to it. Can perform the following operation any number of times. Choose a vertex v which has at least one child. So this means that we can't take a leaf node, increase a v by 1 and decrease a u by 1 for all vertices u that are in the subtree of v. So if we are decrementing the so we can increment the value of a v by 1, but at the same time we have to decrement the value of a u, where u are the nodes in the subtree of the node v. However, after each operation the values on all vertices should be non-negative. The value on all vertices should be non-negative. Your task is to calculate the maximum possible value returned in the root using the aforementioned operations. Yeah, so this is the question. So the two main observations that we have to make over here is these two things. We can't choose a vertex which is a child, so we have to take a vertex which has at least one child. Oh, so we can't take a vertex which is a leaf. So we have to take a vertex which has at least one child. So it means that we can't take leaf nodes. And the values on all the vertices should be non-negative. So these are the two main the solutions that we have to make here in the problem statement. Now I will show you how to solve this particular problem. Uh, okay, okay. Now I will show you for this test case. So what they have mentioned is that we can take a node v, we can increment the value of the node v by 1 plus 1, but we have to decrement every node u in the subtree of this particular node v by minus 1. So this is what it is mentioned in the problem statement. So suppose this is one of the test cases that is there in the problem statement. So what we can observe is that, so the first observation is we can make is that we have to make the value of all the nodes almost similar. So we can see that here the value of 3 is equal to 0 and the value of 4 is equal to 2. So if we try to make it almost equal, then we can increment the value of the root. So since 3 is already equal to 0, we can't perform any operations on the root node, because if we perform a operation on the root node, it will be equal to incrementing the value of the root node by 1. So here it is 0, it will become 1, and we have to decrement the value of all these you know all these nodes in the subtree of the root node by, we have to decrement all the nodes in the subtree of the root node by minus 1. So this will become equal to -1. But in the problem statement, we have been mentioned that it has been mentioned that the values can go below 0. So we can't do that. So what we try to do is that we try to increment the value of node 3 initially. So how can we do that? We will perform the operations on node 3 some amount of time. So after we perform the one operation on node 3, the value this 0 will become equal to 1, and this 2 will become equal to 1, because we are incrementing the value of node 3 by 1, and we have to decrement the the values of all the nodes in the subtree of 3 by uh, uh, -1. So the value of 4 becomes equal to 1, which we obtained by decrementing 1 from 2, and the value of 3 became equal to 1, which we obtained by incrementing 0 by 1. So now we see that, you know uh, none of the all the values in the all the values in the subtree of the root node are almost similar or equal. So now we can perform the operations on the root node. So after we perform a operation on the root node, the value this value will become equal to 1, and all these values will become equal to 0 because we are decrementing all these values. So, and now we have obtained the maximum possible value that we can obtain at the root node, which is 1 after the operation that was mentioned in the problem statement. Now, now I'll give you a more complex test case. So let us try for this test case. Right. Now, what we can see that now we can see that the values at the each of the nodes is like distributed irregularly. So what we can do is that so we can start from the this subtree. You can start from any subtree. I will start from this subtree. You can see that the value of this parent node is like irregular. It is 3, but no, its children have higher value. So what I will try to do is that I will try to make the values in this entire subtree almost similar. So what I can do is that we can't perform any operations on this node because it is a leaf node. We can't perform any operations on this node 8, which is also a leaf node. Alright, so we can only perform an operation on this node. So what I will do is that I'll perform one operation initially. So after I perform one operation, uh, this value will become equal to 4. This value will become equal to 5. This value will become equal to 7. So this will be 4. This was initially what 6, so it will become 5. This will become 7. Now after I perform another operation, this will become 5. This will become 4. This will become 6. But now we see that the value of the parent node gets gets greater than the value of the its children node. It's fine, but I will not try to do that. So I will try to keep it as 4 itself. I won't do the operation. I won't do this operation. So so initially this was 3. I incremented it to 4. Initially this was 6. Decremented it to 5. Initially this was 8. I decremented it to 7. So now the values are almost similar. Now performing any more operations on this subtree won't make much difference because uh, the change will be the same. Now I will consider the subtree rooted at node 2. The subtree rooted at node 2, we can see that uh, the the oh, yeah, the subtree rooted at node 2. We can see that the value of the subtree rooted at node 2 have higher value than some of its children. So we can't perform the operation on this particular root node, on this particular node. Because its children, it's one you can see that three of its children, the node 4, the node 5, and the node 7 have value lesser than the value at the node 2. So if we perform the plus 1 operation over here and the negative 1 operations over here, the irregularity will only increase. So one observation that we can make here is that if the value at the value of the parent child, that parent node that we are considering, is greater than the value of its children nodes, we won't do any operations. Because if we perform an operation over here, this 6 value will become equal to 7, and the value of these children nodes will become equal to, like, they will decrease further and the irregularity will be more. So we won't try to do that. Now we will consider the node 3, the subtree rooted at node 3. We see that there is some irregularity. So what I will try to do is that I will try to make the irregularity lesser. So initially I will increment 2, so it will become 3. I will decrement 8, it becomes 7. I will increment 3, it will become 4. I will decrement 7, it will become 6. I will increment 4, it will become 5. I will decrement 6, it will become 5. Okay, now we have made the irregularity much more regular, so we don't have to do any more operations over here. Now we will reach 3. After we reach 3, after we reach 3, we have to we can perform the uh, we can perform the plus 181 operations as long as it is possible, because like we have made the irregularities in this subtree as minimal as possible. Now we can perform the plus 181 operations on this subtree. So how many times can we perform the plus 1 negative 1 operation on this particular root node? The number of operations that we can perform on this root node will be equal to the minimal value in this particular subtree. So the minimal value in the particular subtree, we can see that it is 5. So we can perform all the plus 1 operation over here uh, as 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 many times as the value of the minimal uh, minimal uh, minimal value of the node in the subtree. So we can perform plus 1 operations 4 times over here. So we will get 3 plus 4, which will be the final answer that we will be returning. And after we perform the plus 4 operation, we have to decrement the values of all all these nodes by -4. So yeah, we can do that. So this will become 0, this will become 1, this will become 1, this will become 3, this will become 1, this will become 1, this will become 2. And you understand why we took plus 4 over here, right? Because like if we do any more operations than the minimal value in the subtree, it will become negative. So we can only perform the operation as long as the minimal value in the subtree. So this is the logic behind the problem. Now I will show you the code for the problem. So this is the code for the problem. So I have the, we are just doing a DFS. It's a very simple code. I will show you the code. Now, initially, I'm creating an adjacency matrix. I'm creating a vals array to store the value of each node, and this is a visited array for the DFS to check whether I visited a particular node or not. I am inputting the vals array. I am I'm creating the adjacency matrix, and I'm calling the DFS. So we start the DFS from the root node, which is 1. It is mentioned in the problem that the root node will be equal to 1. We are passing in the adjacency matrix, we are passing in the vals array, and we are passing in the visited array as well. So when we reach a particular node, we set the visited of the particular node as 1, and the current value of the particular node will be the vals of node. I am storing it in a variable called current val, and I'm initializing a min called a variable called min, and I'm initially setting it as a high value. This min will store the minimal value in the particular subtree of this particular node, and I am checking whether this node is a leaf node or not. Initially, I am setting it as true. If it has some children, I will set the is leaf condition as false. So we know that it is not a leaf. Now, if the particular child is not visited, what we will do is that we will try to find the minimal element in the subtree of the particular in the subtree of the particular node that we are on. So we are going through all the children in our children of our node, and then we are finding the minimal value in the particular subtree. If if the current node that we are on is the root node, or which is equal to the node which has value 1, we will directly return vals of node plus minimum value in the subtree. Otherwise, what we will do is that if it's a leaf node, what we will do is that we will return the current value of the leaf node. Otherwise, if the current value is greater than the minimal value in the subtree, what we will do is that we will return the minimal value, because as we have explained over here. So initially here, uh, the value was 6, but the minimal value in this subtree was 5, I guess. The minimal value in the subtree was 4. Yeah, so here the value was 6, but the minimal value in the subtree was 4. So we can't perform any more operations over here, because like if we perform any operation over here, the irregularity will only widen. The difference will only become more provision. So we can't do any operations over here. So the minimum number of operations that we can perform on this particular subtree will be equal to the minimal value. So that will be equal to 4. Yeah, because the number of operations that we can perform will be equal to the minimum value. So we will return that. Otherwise, if the current value if the current value is lesser than min, if the current value is lesser than min, as in this case here, initially the current value was 2 and the minimum value in the subtree was 8. So here the current value is lesser than uh, the minimum value. So what we'll try to do is that we will try to decrease the irregularity between those two values. So what I will do is that I will try to take the difference between these two. The difference between these two is 8 minus 2 is equal to 6. So the difference is min minus current value. So 8 minus 2 is equal to 6. And now I will add current value plus diff by 2. So difference here is 6, and by 2 is will be equal to 3. The current value will be equal to 2. So current value 2 plus 3 will be equal to 5. So we got the same answer as we obtained over here as well. So that's how we will minimize the irregularity at a particular node, and we will return that, and we will print the answer at the end. Yeah, that's the solution for the entire problem. Hope you understood it.